Hi there. In this video we're going to talk about solving trig equations. So we're going to set up equations involving trig functions and try to solve them. And the variable that we're solving is going to be inside of the trig function, so we're going to have to think about how to do this. All right, and the example that we're going to start with is the example of a spring. A spring follows a sinusoidal motion when you set it into motion. And so this is a good example to look at to kind of get an idea of where some trig equations may come from. Okay, so here we're looking at a mass on a spring. The mass is this little box, and the spring is depicted by this zigzaggy line. And what we're going to do is imagine that we pushed this mass upwards a little bit. We just flicked it up and set it into motion. What would we see? Well, we would see something like this. The object will oscillate up and down. And physics tells us that the oscillatory behavior of this object, if we measured the vertical displacement, it's given by a sinusoidal function. And it would be a great exercise for you to find that sinusoidal function. Now, in order to do that precisely, I'll have to tell you that the object starts at the middle position, at -3, and initially moves upwards. With that information and what you see here, you can see what the amplitude of the oscillation is. You can see the middle line, the middle of the oscillation. You can see the period of the oscillation. Suppose it takes exactly 5 seconds for the object to get from its highest point all the way down and back to the highest point. So if I tell you that information, you can get the model for this oscillatory behavior. And if you want to review that, you can look at one of my previous videos where I discuss sinusoidal models. But if you do that, what you'll get is the vertical displacement y is equal to 2 sine of 2 pi over 5t minus 3. That's the model that describes this. But suppose we wanted to answer some questions about this spring going up and down. Suppose I wanted to know at what times is the object in its highest position? So right up here. We can see it happens more than once. In fact, it happens an infinite number of times. But what are those times? I may also want to know at what times is the object in its middle position, at height -3. And I may want to know at what times is the object at its maybe halfway between its middle and its lowest position, height -4. So these are trig equations that we want to solve. And so that's the goal of this video here, is to solve these trig equations, and hopefully we'll learn how to do this in general by going through this example. Now let's take a look at what we're looking at here. One of the things we want to do is find when the object is in its highest position at height -1. Well, that means what we're doing is we're setting this expression equal to -1. Okay, and if we just use a little bit of algebra here, add 3 to both sides, divide both sides by 2, we see that we get this equation. All right, so this will give us the times when the height of the object is exactly -1. And what we'll do to solve this to begin with is we'll just look at where this is equal to 1. We'll find the values of theta that are equal to 1 and then realize that theta is the same as 2 pi over 5t, and that will give us the value of t. Okay, the other values that we wanted to look at were when the height of the object is -3. So our equation would be as follows. And using a little bit of algebra shows us that this leads to this. And so we'll be looking at where sine of theta equals 0, and then realizing that theta is equal to 2 pi over 5t. Right? And then finally, we'll be looking at where the height is -4. So we'll be setting this equal to -4. And using a little bit of algebra, we get to here. All right, so we're going to be looking at where sine of theta is equal to -1/2, and then converting back to t via the relationship between theta and t. So what we're looking for, we're going to be looking for solving these trig equations, where sine is equal to 1, where sine is equal to 0, and where sine is equal to -1/2. Now, how are we going to get the answers here? Well, that's where we need to look at the unit circle. And I want to point out to you that the unit circle is in the picture that we're looking at right here, although you may not see it. But if we move to the left a little bit, you'll see that this whole picture is generated by a point spinning around a circle. Now, this isn't the unit circle. This is a circle of radius 2. But the idea is the same. The height of the object on the spring is given by the height of the point as it spins around the circle. And so we are going to be looking for when the point is at its highest position, when the point is in the middle here, which actually occurs at 2 points there, and when the point is halfway down here. So it actually occurs here and here. Those are the values that we're going to be looking for. So let's go to the unit circle and do this analysis. Okay, so here we are looking at the unit circle. We're going to try to use this to solve the equations that we had just mentioned. Let's start with this equation. I think this will be the easiest for us. Sine of theta equals 0. How can we solve this equation? Well, what I'm looking for are angles, those are values of theta, that put me at points whose height is 0, because sine gives me the height of the point. All right? Well, this point right here has height 0, and so does this one. What are their angles? Well, this point is at angle 0, and this point over here is at angle pi. Are those the only angles? Well, no, because we can go pi, but we can also go 2 pi. 2 pi is another angle. And I can go one more pi and go to 3 pi. Or I can go 1 pi, 2 pi, 3 pi, 4 pi. In fact, any multiple of pi will work. And in fact, I don't have to just do positive multiples. I could do negative multiples. I could go clockwise pi, that's negative pi radians, or negative 2 pi radians, or negative 3 pi radians, or negative 4 pi radians. So we also have these angles. All these angles are the solutions to this equation. Now, writing out an infinite list like this is a little bit tedious. It would be nice if we could encapsulate that in a nice little expression. And in fact, we can. What am I looking at here? I'm looking at all integer multiples of pi. So I'm looking at k times pi, where k is any integer. And if I do that, if I take any integer for k and plug it into this expression, I will get one of these. And all of these can be obtained this way. So this characterizes all of those solutions. So this is how we would answer this question. Okay, another equation that we were looking at was sine of theta equals 1. What are the solutions to this? Well, now I'm looking for points whose height is 1. Well, that's this point right here. And there's no other points on the unit circle, so it's just this one. What's the angle that gets me there? Well, it's pi over 2 radians. So I can see that one solution is pi over 2. But is that the only solution? Well, no, because we can go pi over 2 and then come all the way around again and come to here. How many radians is that? Well, that's pi over 2 plus 2 pi. Well, 2 pi is 4 pi over 2, so 4 pi over 2 plus pi over 2 is 5 pi over 2. So by adding 2 pi to this angle, I got another angle. And I can add 2 pi again and come around again. That is 9 pi over 2. And if I add 2 pi again, 13 pi over 2. In fact, I could just keep going. This goes on and on infinitely many times. And I also can do negative angles. I could do negative 1 pi over 2, 2 pi over 2, negative 3 pi over 2. Notice that's the same as just subtracting 2 pi from pi over 2. Gets us here. And if we subtract 2 pi again from this angle, I end up with negative 7 pi over 2. And if I subtract 2 pi again, I end up with negative 11 pi over 2. And if I subtract 2 pi again, negative 15 pi over 2. And it goes on and on and on. So I have infinitely many answers here. So just like we did with the last equation, we'd like to encapsulate these into a nice, neat expression. Well, what did we do to get all these? I just took pi over 2 and I added multiples of 2 pi, integer multiples of 2 pi. So I'm going to write that. Pi over 2 plus 2 pi k, where k is any integer. And this encapsulates all of these possible solutions. If I take any integer for k, I will get one of these, and any one of these can be found by taking the appropriate integer value of k. So that is how we would answer this equation. All right, the other equation that we wanted to solve was this one, sine of theta equals -1/2. So now we're looking at points whose height is -1/2. Well, there's this one over here, and there's this one over here. How do we describe these? Well, let's just see what their angles are. Well, to get to this one, I can see it's 7 pi over 6, right? So I could just take theta equal to 7 pi over 6. To get to this one, I'm actually going to write another line here, 11 pi over 6. Okay, so moving on, how do we get to the next ones? Well, if I go 7 pi over 6, I can go another 360 degrees, 2 pi, and I land again at this point. 2 pi is 12 pi over 6, so just add 12 pi over 6 to this. And that gives me 19 pi over 6. And if I add 12 pi over 6 again, I end up with 31 pi over 6. And we can keep going. Now we can do the same thing for this one. I have 11 pi over 6, add 2 pi, add 12 pi over 6, and I end up with 23 pi over 6. Add 2 pi again, and I end up at 35 pi over 6. And I keep going. I get more solutions. So we see there's infinitely many solutions. And I could go to negative solutions too by subtracting 2 pi over 6 from each of these. Right? So we could extend these into the negative realm as well. Now, how do we describe these? Well, you'll see that there isn't a real nice consistent way to get both lists at the same time. So we're going to have to write two separate expressions. All right, and we're going to put an or in between them. So that's what we're going to do. Let's think about this first expression. I started with 7 pi over 6, and I added multiples of 2 pi. So theta equals 7 pi over 6 plus 2 pi k. And how did I get these? Well, I started with 11 pi over 6, and I added 2 pi k. Now, what is k? You can't just throw out a variable that means something without telling people what it means, right? So we have to write that, where k is any integer. And so these pair of formulas give us the solutions to this equation. Take any integer for k, and these will both be one of these numbers. And if you take any of these numbers, you will find an integer k so that it's one of these, right? So this really describes all possible solutions. So we can see that sometimes you actually need to write down two expressions. It turns out in these problems, you'll always be able to, when you have it in the form sine theta equals something, you can always get away with at most two expressions for theta. But you might, like in the previous two problems, get away with just a single expression. Now, I'll also point out that these starting points that we chose, 7 pi over 6 and 11 pi over 6, those are not necessary that we chose these particular values. We could have chosen any value. All right, so there's more than one way to write these down. I could have started at 19 pi over 6 for this one, and I could have started at 23 pi over 6. Or I could have started at negative pi over 6 for this one, and negative 5 pi over 6 for this one. Those would also be valid answers because they generate the same lists. So you'll see there's actually more than one way to write these down. Okay, so here we are back at the spring problem. All right, so we were looking for, one of the first things we were looking for was when the spring is at its highest point. All right, so what we did is we set up this equation. We set the displacement function equal to -1, that's the highest position. And we used a little bit of algebra, and we said that, okay, we need to solve sine theta equals 1. All right, well, we just did that, right? When we solved sine theta equals 1, we found that theta is described by one of these values here, where k is any integer. But what we're really after is the value of t. All right, so how do we find t? Well, remember that theta is equal to 2 pi over 5t, so just plug that in over here in place of theta and solve for t. So I'll just divide both sides of this equation by pi and multiply by 5/2. And so what I find is that t is equal to 5 pi over 4 plus 5k, where k is any integer. So this is my solution here. I would write my solution like this. These are the times where the mass is at its highest position. All right, the next thing we looked at is when the object is at height -3. All right, so we set our displacement function equal to -3, used a little bit of algebra, got this equation. We realized, okay, well, we'll think about sine theta first, and we see that the solutions to that are as follows. But now let's go back to t. So just like before, theta equals 2 pi over 5 times t, so plugging that over here and solving this equation for t shows us that t is equal to 5/2 k, where k is any integer. And so that is the solution. These are the times when we are going to be at this middle position. So if you were asked to solve that equation, this is what you would get as an answer. There's actually an infinite number of times that give us solutions. In fact, we can say that, 5/2 is 2.5, right? So every 2.5 seconds, every multiple of 2.5, we will be at this position. And that makes sense if the oscillation happens over a 5-second period. And finally, we wanted to look at when the height was equal to -4. All right, so what we did is we did a little bit of algebra on this equation here, simplified it to this, just plugged theta in place of that expression, and we found that the solutions for that were a pair of formulas we got for these. So we're going to solve these for t, because what we're really after is time. All right, so let me slide things over a little bit, and we'll just come over here and write everything in terms of t. All right, so I'm going to replace theta with 2 pi over 5t, and then solve these, which means I'm going to multiply both sides of these equations by 5 over 2 pi. So what I get here is I get t equals 35 over 12 plus 5k. And for this one, I get 55 over 12 plus 5k. And again, where k is any integer. And so this is how I describe the set of all solutions to this problem up here. These are the times when the spring is going to be at position -4. And really, I should put an or in between these, because t could be this or this. All right, so there you go. I hope this video helped you see why trig equations are useful and how to go about solving them. So thanks for stopping by, and I'll see you in the next video.